Okay, excuse me. So 12.2 is all about chords and arcs. So first thing we're going to talk about is just what is a chord. A chord is just a segment as opposed to a line, right? Chord is going to have endpoints to it. And those endpoints are going to be on a circle. So if you look here, there's a point, a point here P, a point here Q. Okay, those are your endpoints. The segment PQ then is your chord. So the chord is segment PQ. Notice just has the bar over top. But then there's also an arc that's related to your chord. And I think you can probably see what that arc is. That would be this arc here. Okay, so we call that arc PQ. Notice that one has the little arc over top. So just make sure when you're naming things, you put the arc. If it's an arc, you put the line, the straight line, if it's a chord, okay? The segment, if it's a chord. Okay, so that's chords and arcs, what they are. There are 3 theorems that go along with chords and arcs and central angles, really. These 3 theorems are very circular, very like one thing impacts the other, which impacts the other, which brings you back to where you started. So if you know one, you kind of know all 3 type of thing. But I'm going to give you all 3 just so you see what we're talking about. This first one says, if angle AOB, so that would be this angle right here, is congruent to angle COD, that would be that angle, then what happens is their arc, we call it the intercepted arc, their arcs will always also be congruent. So arc AB would be congruent to arc CD, okay? And you can also flip that around. If their arcs are congruent, then their central angles will be congruent. So the theorem says this: within a circle or in congruent circles, congruent central angles have congruent arcs. Okay, so if the central angles are congruent, like you see here, then the arcs are going to be congruent as well. Okay, so that's the first one. The second one says, if angle AOB is congruent to angle COD, so if these 2 angles are congruent, then the chords across from them are also congruent. So now I'm going to stick with red here. Chord AB and chord CD will be congruent. So congruent central angles have congruent chords also. Okay, and vice versa. Congruent chords have congruent central angles. And then the last one kind of puts that together. Within a circle or in congruent circles, congruent chords will have congruent, any guesses? Arcs. Okay, so basically they're saying if AB is congruent to CD, then arc AB will be congruent to arc CD. Okay. And then right below that, it says, note, all of the converses are also true, which is what I just told you. So the statement and its converse, right? Here's the original, here's the converse. They're both true statements. You can do it either which way. Questions on that? Okay, then take a look at this. You are given this picture, and I want to know what you can say is true based on what we have in this picture. If they don't tell you that you're not going through the center, most of the time it'll be like a little dot here. But even if there isn't a dot there, like on the tests and quizzes that I give you, you can assume it's going through the center if it looks like it's going through the center, okay? So that is the center of the circle. Can anyone tell me something we know about this picture? Do you see any angles that are congruent? Which ones? Let's give this a name. We'll call this O. That might help you a bit in naming things. Yeah, Jonathan.
Angle ROP is congruent to VOT.
Yes, we know that angle ROP is congruent to angle VOT. Why? Because they're vertical angles. Okay, so because we have vertical angles, we have congruent angles. So then what else do you know to be true in this picture? If central angles are congruent, what else is congruent? The arcs. Okay, so we could say VT, arc VT, is congruent to arc RP. What else do we know? If the arcs are congruent, what else is congruent? The chords would have to be congruent, right? So arc RP and arc VT make chord RP and chord VT also congruent. Okay, so if the angles are congruent, then the arcs are congruent and the chords are congruent. So you don't have to be told those things. As long as you know one of them is true, all three of them will be true. Okay? Okay, second little theorem here then. God bless you. Says this: within a circle, or you can have two separate circles as long as they're congruent circles, chords that are equidistant. What does equidistant mean? Equal distance, yes. Chords that are the same distance from the center are congruent. Okay, basically what they're saying there is you have your center of your circle and you have these two chords, chord AB and chord CD. Okay, if the distance to those chords is the same, so if this distance is the same as this distance, remember distance is always perpendicular, so that's why they put the right angles in. If those distances are the same, then the chords are the same. So basically what we're saying is AB, chord AB, is congruent to chord CD because EO was congruent to OF. Okay, so if the distance to them is the same, then the chords themselves have to be congruent as well. Okay? Questions on that? Okay. Then let's try a couple. Don't be surprised if these feel terribly easy to you, okay? Some of these are just like, is that even a question? But it's getting you to use it in other things that we do down the road as well. So bear with me if you're like, this is silly that we're even answering questions like this. I know, some of them just are that easy. Take a look at this one. Technically, we should have marked this as right angles. So because those are the same distance, this is a length of 12, which technically should be more like that. So it's the whole thing. That whole chord is a length of 12. And I'm looking for the length of A. So this chord right here. What would that be? 6, right? 6 and 6 is going to give you 12. Because the distance to them is the same, then the chords themselves must be the same. Am I losing you, Kate? Okay. So A would be 6, okay? Look at example 3 here. It says find AB. So we're looking for the length of AB. How long is this chord? What do you think? It's not 10, it's 20, right? If this portion of it is 10, and these are marked congruent, since the distance to them is both 8, then the chords themselves would have to be congruent also. So because this one over here is 20, then AB will be 20 as well. Okay? Questions on that? That's it for the first one. I know, lovely, right?
Why is it AB 20?
So because they mark these congruent, right? And this one is 10, that means this one's going to be 10 also. So this whole chord is 20. And since the distance to it is the same, to get to this one is 8, to get to that one is 8. If the distance to them is the same, then the chords themselves have to be the same. So that means AB has to be the same as this one. Okay? Okay. Keep going. Finish 12 2B or take a break.
Keep going.
Keep going is the general consensus. Okay. 3 more theorems doing the same thing we did the last time, where one impacts the other, which impacts the other, which brings you back around to the first one. So very circular, right? They all kind of say the same thing with a different piece left out. Here's the first one. In this picture, it says, in a circle, if a diameter is perpendicular to a chord. Okay, so here's a diameter that is perpendicular to the chord. Okay, if a diameter is perpendicular to the chord, then it blanks the chord and its arc. It bisects, okay? So if it's perpendicular and it goes through the center, it's a diameter, then those two pieces are congruent. CE is congruent to ED, and arc CA is congruent to arc AD. Okay, so if you know the red, then you know the blue, is basically what we're saying. Look to the next one. This one says, in a circle, if a diameter bisects a chord, then it is perpendicular to the chord, okay? So now this one is saying, I know it's a diameter, and I know the chord got broken into equal pieces. Therefore, I know that this will be a right angle. So if I know the red, then I know the blue to be true. Okay, if it's a diameter and it bisects, it will be perpendicular. I bet you can tell me the last one. The wording on this one, I guess, is different, but it's really saying the same thing. In a circle, the perpendicular bisector of a chord contains the blank of the circle. It is the diameter of the circle. It contains the center of the circle. So because they told us that it's perpendicular and it bisects, right? Then we know that that is a diameter. It goes through the center, okay? So like I said, all very much one affects the other. I think you'll see you pretty much do the same process on all of these problems. Let me show you what I mean. So look at example 1 here, letter A. It says find the value of x to the nearest tenth. Again, if they don't tell you it's a center, you are allowed to assume center. So this is the center of the circle, okay? How could you find x from this? Tell me what you know. Think of it as if this kept going, right? It would be a diameter. What is it doing? Bisecting, okay? So this is going to be 6 and 6. How do you find x? Pythagorean theorem. You're going to do a whole lot of Pythagorean theorem again today. A lot, okay? So you have a right triangle. You're going to say 5 squared plus 6 squared equals x squared. Remember, the one across from the right angle is always your C, always the standalone. So 5 squared plus 6 squared is 61 equals x squared, and then you're going to square root that. So x is approximately, if we go nearest tenth, which is what it asked us to do, that would be 7.8. All right, look at letter B. This one is a little bit different. Tell me what you know that maybe isn't marked for you.
Bisecting the
X is bisecting. So you have 5 and 5. Diameter is not 10. The chord is 10. Diameter would be 18. Yep. We don't really need a diameter, but the diameter would be 18. This is a radius, right? Here's your center. 9 would be your radius.
the center to the output, the topmost of the triangle, that side would equal 9.
This side would equal 9?
Yeah.
Because it's a radius, right? So we know this is 9 because it's a radius, just like this is a radius.
And then you could do Pythagorean.
Why can we do Pythagorean theorem right now? Because it's a right triangle. This has to be a right angle because this goes through the center and this gets bisected, right? Because it got bisected, it makes a perpendicular. So it's going to be x squared plus 5 squared equals 9 squared, right? A squared plus b squared equals 2 squared. This is where a lot of people made mistakes on the test. Be careful with this. If I take away 5 squared, is that 4 squared? No, right? 9 squared is 81. 5 squared is 25. 81 minus 25 is 56. Just plug it into your calculator. 9 squared minus 5 squared, 56. And then from there, then you can take the square root. So x to the nearest 10th is 7.5. Okay. All right, you try C. See if you can figure out what to do on letter C there. It looks a little different, but you've done this process. Anyone have an answer? What'd you get, Jonathan?
Equals to 10 point something.
10 point something. Anyone get the something?
10.2.
10.2. 10.2 is right. What do you do here?
11 squared plus x squared equals 15 squared.
Yeah, you can move your radius, right? No matter where you put a radius, it's still the same length. So if we move our radius, either down here, or you could move it on the top one too, that length is still 15 because this is my center. That makes it a radius to go all the way to the circle. This has to be perpendicular because it bisected that side. So we have x squared plus 11 squared equals 15 squared. So take away the 11 squared, not 4 squared, right? This is x squared equals 104. And then take the square root of that, and x comes out to 10.2. Lots more Pythagorean theorem again, right? Okay, the last one. I'm going to warn you right off the bat that a lot of people do this one wrong because of algebra, not because of geometry. You are welcome, if you want, to call this piece right here half of x. But I will tell you right now that 90% of the people that do call that half of x get the wrong answer. Here's why. If you take this as 1/2 of x, people go, oh, 1/2 of x squared is 1/2 x squared. What is 1/2 of x squared?
1/2 times x, then e squared.
No. Unless I heard you wrong, because you guys were both talking at the same time. It's this, right? What is 1/2 x squared? It's 1/4 x squared, right? So if you want to do it that way, fine, but it's 1/4 x squared once you square the 1/2, okay? So that's up to you if you want to do it that way. Here's what I recommend. If I were you, if I were sitting in your seat right now as a high school geometry student, this is what I would do. This is a right triangle. And I need the whole thing, but I'm going to find this first by just calling it a different variable. Call it y, okay? If I set this up, y squared plus 4 squared equals 6.8 squared, then I can just plug it in, take away the 4 squared. So I get y squared equals 6.8 squared minus 4 squared should be 30.24, okay? Then take the square root of that. So y equals 5.499. I'm going to round to 3 decimal places because I'm not done. That's not my answer. What's my answer? What do you do to that?
Times 0.5.
Not times a half. You double it. Times 2, right? I just found this. I want to know what x is. I want to know the whole thing. So if I just found y, I'm just going to take that and multiply by 2. And my x value then is going to be 11.0 for the length of that chord. Does that make sense? So you're welcome to do it this way, but if you do it that way, please call it 1/4 x squared, because that's what happens when you square 1/2 x, 1/4 x squared. And then you'll be just fine. Questions, comments, concerns, accolades? You love me? You're going to miss me terribly for the next 5 days? No? Okay. That's all we have